Yeah, I'm loving it. Hey guys, what's going on? This is not sponsored by McDonald's. However, we're talking about loop quantum gravity. Why is this? Well, while serving the cosmic wave function of the internet, of course I came across a Wolfram stream. I totally didn't share audio because I was planning on doing something else for that. I was going to show the actual loop quantum gravity. This is why live is a wonderful thing. Now, since the audio is shared, roll that beautiful bean footage.
One object that you can, so the parameter would be the coupling constant of string theory.
Oh.
There's a coupling constant.
A coupling, you
which
say?
Is the string tension, basically.
No, the string tension
This is interesting.
Is dimensionful.
Okay.
It's the strength with which it tells you the likelihood for one string to split into two.
Okay.
Oh.
Okay. So you can dial that parameter.
Mm-hmm.
And so you have an object which we found an object which has the property that for one value of the parameter, the best description of it is as a black hole, is to use the Einstein equations and describe it as a black hole with an event horizon and an entropy that can be computed using the Bekenstein-Hawking formula.
All right, that was the other formula I was looking for, because I was looking for the actual functions and stuff he was mentioning before in Wikipedia. Why do I say this? Well, essentially they're talking about loop quantum gravity, which is essentially what I call harmonic oscillation, just because it's all oscillatory, bro. Now, we're not going to do any intro or anything like that. I actually am so late right now. It's all right, I feel like a white rabbit. But if we pop over here, we'll share the full window here. And as we can see, loop quantum gravity is a theory of quantum gravity which aims to merge quantum mechanics and general relativity, incorporating matter of the standard model into the framework established for the pure pure quantum gravity case. It is an attempt to develop a quantum theory of gravity based directly on Einstein's geometric formulation rather than the treatment of gravity as a force. As the theory LQG postulates that the structure of space is composed of finite loops woven into extremely fine fabric or network. These networks of loops are called spin networks. The evolution of a spin network or spin foam has a scale in the order of the Planck length. Oh, the Planck length, you say? Approximately 10 to the minus 35 meters, and small scales are meaningless. Consequently, not just matter, but space itself prefers an atomic structure. All right. And then, wait for it. Oh, what's that? The simplest non-trivial Mandelsom identity relating to different Wilson loops. Loops we're talking about now. Oh, very interesting. We go through the Hamiltonian, which seems to be a mixture of electromagnetism and temperature there. And this seems to be really big within the black holes and stuff like that, because this is something that we seem to be able to calculate. We seem to be able to have an observation and figure this out. So if we have something that we know, then we can try to derive everything else. Oh, look at this beautiful, and it's morphing into 3D space. If I didn't know any better, that seems like a tetrahedron. The hyperbolic figure eight knot. It's composed of two perfectly isometric tetrahedrons, I believe. Or at least two perfect tetrahedrons. Maybe it's complement. I forget. Spin foam and everything, so we'll pop over here, because he was talking about the coupling constant. All right. A coupling constant or an interaction constant is a parameter in the field theory which determines the relative strength of interaction between particles or fields. In the quantum field theory, the coupling constants associate with the vertices of the corresponding Feynman diagrams. Oh. You mean basically this stuff? The path interval? Oh. Like that's something that Professor Feynman often spoke about. Dimensionless parameters are used as coupling constants, as well as quantities associated with them that characterize the interaction and have dimensions. The examples of the dimensionless fine structure constant of electromagnetic interaction and the electric elementary charge measured in the coulomb. Oh. I'm pretty sure that's the third or fourth articulation of the hyperbolic figure 8 knot, or at least that's what it calculates out to, I believe, the Planck charge. Now, all I'm saying is let's pop over the spin foam because it's actually beautiful and I use that for a thumbnail. Total simulation. Their thingy should be in the doobly-doo. But yeah, simulated Large Hadron Collider right there. Oh, it looks kind of loopy. Kind of looks like 3 kind of things you see there. I don't know. I believe this is what we call quarks, or basically when we smash 2 protons into each other fast enough that basically it just is going like 9.99.9999 whatever times the speed of light. I remember calculating something like this in college. I took modern physics for like a week or so. But yeah, basically it's like, all right, we've detected the Higgs field. That's the thing that's kind of binding them together there. What do we have to do? We had to accelerate it to an absolutely wicked fast speed and have them bump together to try to break them apart. Now, I'm not saying that this is necessarily the hyperbolic figure 8 knot, but all I'm saying is when we go to the hyperbolic figure 8 knot, I don't know. You see that? Again, none of this is absolutely confirmed. I don't know. What do we all think? And I see you there. Oh, welcome, Lewis. Good to see you. Hey, we're looping all around. We were discussing a broad variety of topics here, my friend. Now, with that all done, we'll actually finish off. Because remember, we were talking about the fine structure constant. That seemed to be important to us. So we'll go back to our Chrome tab and share Thad's video.
In this chapter, we identify the remaining actions of this partition balance, revealing the geometry that defines the balance of each unique boundary intersection within the hyperbolic figure 8 knot. We discover that every unique partition balance defines a constant of nature.
Oh.
Therefore, every constant of nature is uniquely defined in terms of the hyperbolic figure 8 knots partition constants and uniquely defines one of the balances of those elementary partitions.
Really?
So we've got a balance template here so that if you want to spend time really looking into the constants of nature and
I'm just saying this was put out here before the muon G2 results.
Boundaries are involved.
That's all I'm saying.
This balance template should help. First of all, the symbol on the left would be the constant of nature that you're talking about, right? But it'd always be broken into a primary boundary and a terminal boundary action. If there's 2 of them involved, it could be just the primary one.
Okay.
There's going to be some geometric primary action. In this case, when we have the Compton wavelength as our template, okay, then the primary action is just 2 pi. It's pretty easy to interpret geometrically.
2 circles.
The boundary of that
or 1 circle
is playing on is
that a map?
Length times by the Planck mass over the mass of the electron. Okay, so that
the mass of the electron. Now, there's a lot of electrons released.
The boundary, of course, is always the Planck length times the Planck mass divided by the Planck charge squared.
Okay.
It has a terminal action, another geometric expression out in front of it. In this case, it happens to be the alpha Feigenbaum constant, our splitting coefficient, times by b over 2, 7 over 2, right? That's our Rake and scale symmetry split. Okay, great. Also a beautiful equation. All right, well, when we go through here we go. The fine structure constant, the number that Dirac perfectly pointed out, we're not going to make any progress in physics until we understand this number. This number.
Okay. The fine structure constant, as modern physics knows it, as far as I understand, is the one that goes down with the brackets there. The one in the green here, that's Thad's prediction based upon his analysis of the hyperbolic figure 8 knot. Looks like he's within the error bars. I'm just saying.
Geometrically defines a squarely intersected hyperbolic vortex. Right? That's the arrangement we have. If you take the first solution of the hyperbolic vortex, square it, you get the fine structure constant. Continuing.
We don't need to continue. If you want to watch it, that's video, source code 7. Again, that premiered about 12 hours or so before the Muon G2 results were actually, like, unsealed from the envelope. Yeah. All I know is Professor Wolfram spent about an hour yakking on about turbulence and why it's important in physics. I don't know if you can solve the hyperbolic vortex equation. Can we solve loop quantum gravity and string theory now? I think we might be getting there. I should actually do some calculations. I apologize. Hello there, Dandelion Fluff. I see you there, Gibbler. Welcome. Thank you all for joining. And hopefully in the future, this video will make more sense. Peace out, everybody. Be safe. And no matter what happens, remember, come on and get your log. Everyone needs a log. Come on and get your log. Everyone needs a log. Log from Blammo. This video is also not sponsored by Log nor McDonald's. So yeah.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.